This is a look on electronics behind logic gates. This is a 74HCT04 6 NOT gate integral circuit. It's powered by 5 volts at 14 pin and grounded at 7th pin. It has 6 inputs and 6 outputs. Therefore, it's made out of 6 NOT gates. The A's shows the inputs and the Y's shows the outputs. The number signifies which gate it is. Looking at the truth table, can be seen that the output is inverted input. More on that in my previous tutorial in the description. As the output indicator, I'll be using green LED, which does not need resistance for 5 volts for easier understanding. So at the first pin, the input is low, so the output is high on the second pin, as the LED shows by shining. On the third pin, the input is high, so the output on the fourth is low. Here I am using jumper cables to directly give high or low input, and as before, when the input is high, the output is low, and the other way around. 74HC08 is a quad AND gate integral circuit. You can see the pin configuration here. The powering of this IC is the same as the previous one. One gate consists of an A, B, and Y. The A and B being the inputs and Y being the output. And the gate has a high output only when both inputs are high. And again, you can find more on logic gates in my previous video. The quad AND gate is second from the left. First and second pins are both connected to 5 volts. The both inputs are high, so the output pin 3 is also high. Fourth and fifth pins are low, so the output is also low. 13 is low and 12 is high, so 11th is low. Using jumper cables as inputs for the third AND gate and LED as the output, you can see that the output results are the same as before, as shown in the truth table. Keep in mind that when not both inputs are connected to somewhere, the output might glitch. ls00, a quad NAND gate. What's the difference between LS and HC, you might ask? In short, the difference is in the manufacturing technology. The LS is an older version. So again, A's and B's are inputs as can be seen, and Y's are outputs. This is a inverted AND gate, so outputs are inverted and outputs. So when both inputs are connected to 5 volts, the output is low. When both inputs are connected to ground, or when one of the inputs is high, like in the fourth gate, the output is high. Here I'm struggling with the jumper cables again. The jumper cables are a good way to check if everything is correct. And of course, the outputs of the third gate responds correctly to the truth table. Only when both inputs are high, the output is low. 74HC02 is quad NOR gate. It is a inverted OR gate. And if you're considering that I skipped OR gate, don't worry, I did not. The main difference in this IC is that the output is before the inputs. By that I mean, looking at the first gate, the output is on the first pin and the inputs are on the second and the third, and that might be a bit confusing. On the breadboard can be seen that both high inputs output a low signal and both low signals output a high signal. And when one of the inputs is high and the other is low, the output is low as well. Then, of course, I am connecting the jumper cables for whole eternity, and you might not think that, but using a pair of tweezers for an entire video is pretty damn hard. However, we can see that the outputs are as described as in the truth table before. 74HC86 is a quad XOR gate. The pin assignment is shown. This IC outputs 1 only when the sum of both inputs are equal to 1, meaning that only one of the inputs must be connected to 5 volts and the other is to ground. Pin 14 and pin 7 is VCC and ground by the same order. So if the both inputs are 5 volts, the output is low. If the both inputs are connected to the ground, the output is also low. However, if one of the inputs is connected to 5 volts and the other is to the ground, the output is high. Then that can be seen on the fourth gate of this IC. Now jumping to jumper cables, we can see the same result. 0, 0 is 0, 1, 0 is 1, and 1, 1 is 0. Now moving on, I did not have a OR IC, so I'm going to show you how to get the outputs of OR with NOR and NOT gate. Cause connecting NOT gate after NOR gate, you will get the outputs of a simple OR gate. It's like double inversion is equal to no inversion. So here I have connected the outputs of NOR gate to the input of NOT gate, and I'm getting the outputs of OR gate. 1, 1 in NOR is 0, and after NOT gate is 1. 0, 0 in NOR is 1, and after NOT is 0. And 0, 1 in NOR 0, and after NOT 1. So the same trick with the XNOR gate, since I don't have it, except this time it's not double inversion but a simple inversion, cause XNOR gate is simply inverted XOR gate. So the outputs of XOR are connected to NOT gate inputs, and the NOT gate outputs will be the outputs of XNOR. 1, 1 is 0 in XOR, but 1 after NOT. 0, 0 is 0 in XOR, but 1 after NOT. 0, 1 is 1 in XOR, but after NOT it's 0. So the outputs are the outputs of XNOR truth table.